Okay, we're starting on lesson 1.5. These are complex numbers. As we learned, there are some quadratics which have no real solutions. Okay, we talked about when you have a negative number for your determinant, that is under the radical sign in your quadratic equation, your quadratic formula, you don't get any real solutions. You have what we call complex solutions. For example, x squared plus 1 equals 0 has no real solutions because there's nothing you can put in for x here that's going to give you -1, so that when you add it to +1, you get 0. So there are no real numbers that you can put in that will be solutions for that equation. However, mathematicians created an expanded number system called the imaginary numbers, or really the complex numbers. I think what I want to say is complex. Let me just change that because that is really what I want to say. So the complex numbers, and part of the complex number is the imaginary part. The word imaginary makes you think that these numbers aren't actually, they're somehow less real than the real numbers. But numbers are just ideas anyway. You can't pick up a 3 and hold it. You can hold this curvy thing that we use to represent 3. You can hold 3 cookies. You can have 3 friends, but you can't have, 3 is not a concrete object. It's an idea. Threeness, it's an idea that we think about and manipulate, but it's not a real thing that has some kind of concreteness to it. We say real numbers because we're talking about things like age and temperature and how many cookies you have or whatever, and that seems real to us. And then when you talk about numbers like the square root of -1, that doesn't seem real, but it has applications that are just as real as any of the applications of the real numbers. You have to have the complex numbers to do a lot of things that we do with technology and chemistry and rocket science, all that stuff. So they're just as real. They're just another number system that we can use to manipulate. So the imaginary unit I is equal to the square root of -1. So the square root of -1 is just the imaginary unit, and if you square a square root, you get the number under the square root. So I squared is -1. Okay, we created this idea. Euler, the mathematician Euler, who was a believer, by the way, came up with this idea to write it as I. That's called Euler's number. And so I squared is -1, and in order we use this in order to deal with lots of different issues, especially when we get a quadratic that has roots that have a negative under the root. Each number in the complex numbers is made up of a multiple of I plus a real number written as A plus BI. A is the real part and BI is the imaginary part. All right, so when A equals 0, we have an imaginary number. So if there is no real part, it's just an imaginary number. And when B equals 0, we just have a real number. If there is no imaginary part, then you've got a real number. For instance, we would write the complex number -5 plus the square root of 9 as -5 plus 9i, the square root of 9i. Okay, because the square root of 9 is the square root of 9 times the square root of -1. So whenever we have a negative number under the square root, we rewrite it this way, which is just square root of 9i. I is the square root of -1. So this is how the standard way you have to deal with any number that has a negative under the square root. You have to rewrite it as a positive number under the square root with this I. Okay, so two complex numbers, A plus BI and C plus DI, are said to be equal if A equals C and B equals D. So it's pretty obvious. Two complex numbers are equal if they have the exact same coefficients, the exact same real part and the exact same imaginary part. All right, so I'm just giving you the information about our complex numbers, explaining how they work. We know how real numbers work. Now we're going to talk about how complex numbers work. So two complex numbers are said to be equal if the real parts are equal and their imaginary parts are equal. We can add complex numbers. You do it just the same way you would add like terms. Okay, so you add the real parts, you add the imaginary parts. So when you add two complex numbers, like in part A here, you add the real parts. 4 plus 1 is 5. You add the imaginary parts. 7i minus 6i is just 1i. So 5 plus I is what you would get there. Here, 3i minus the quantity negative 2 plus 3i. You have to distribute the negative sign just the same way you would do if these were x's instead of i's. So 3i plus 2 minus 3i. And you can see 3i minus 3i is just 0, so we get 2. Over here, we've got 3 plus 2i. We've got 4 minus I, and then you've got to distribute the negative sign, minus 7 minus I, and then you just add the imaginary parts and you add the real parts. So the real parts, 3 plus 4 minus 7, that's just 7 minus 7, which is 0. So all those go away. Then 2i minus I minus I, that's 2i minus 2i, which is 0. So that all came out to be 0. So adding complex numbers is pretty simple. Just add the real parts, add the imaginary parts. To multiply complex numbers, you just use the distributive property, just the same way you would do if I was an x. So in part A here, 4 times negative 2 is negative 8. 4 times 3i is 12i. So negative 8 plus 12i. When you have two binomials, you have to FOIL it, just like we do with any other two binomials. So 2 times 4 is 8. 2 times 3i is plus 6i. I times 4, negative I times 4 is minus 4i. And then negative I times 3i is negative 3i squared. All right, so you have your real part here. You have 6i minus 4i, which is 2i. And then you have this 3i squared. Now, what is I squared? I squared is negative 1. So negative 3 times negative 1 is what you've got right there. So 8 plus 2i plus 3. So your final answer will be 11 plus 2i. Always write the real part first and the imaginary part second. This is critical and crucial, and it's not okay to write it either way. You have to write the real part first and the imaginary part second whenever you write a complex number. All right, what happens when we multiply a complex number by its complex conjugate? Well, we get a difference of squares the same way we do when we multiply two conjugates that have real numbers or x's and y's, but we'll just multiply it out to show you that it does work. So a times a is a squared, and then you would do first outer, so that would be minus abi, and then plus abi, and then minus b squared I squared. So these cancel, and then you end up with a squared minus b squared times I squared is negative 1. So in this case, you end up with a squared plus b squared. So it's a little tricky because you always have to remember I squared is always negative 1 because I is the square root of negative 1, and the definition of square root is the number you multiply by itself to get the number under the radical. All right? So got to be really careful when you're dealing with your i's. All right, if we multiply each complex number by its conjugate, let's see what we get. All right, 1 plus I, if you multiply by its conjugate, it's just 1 minus I. When you multiply complex conjugates, you get a difference of squares. So this is going to be 1 squared minus I squared, which turns out to be 1 minus negative 1. So it's 1 plus 1, which is 2. All right, when you multiply 4 minus 3i times 4 plus 3i, again, I can multiply it all out like I did up here, but those middle terms are always going to cancel. Whenever you multiply conjugates, that means two binomials where the middle sign is different. Middle sign is opposite. These are not opposites, they're conjugates, okay? 4 minus 3i, 4 plus 3i. When you multiply complex conjugates, you get a difference of squares, just like you do, if you multiply a plus b times a minus b, you always get a squared minus b squared. Same thing happens with complex conjugates. 4 minus 3i times 4 plus 3i is 16 minus 3i squared. So 4 squared minus 3i squared, which is 16 minus 9i squared, which is 16 plus 9, which is 25. So I squared is always negative 1. To divide complex numbers, you simply rationalize the denominator. Okay? You might say, well, why do I need to rationalize the denominator? There's not a square root in there. But there is, because I is the square root of negative 1. So whenever you have complex numbers and you have a complex number in the denominator, you do have a radical in the denominator. So you have to multiply the top and the bottom of that fraction by the conjugate of the denominator. So you multiply the top by 4 plus 2i, and you multiply the bottom by 4 plus 2i. All right, so on top, you just multiply it all out. First outer, inner, last, so 8 plus 4i plus 12i plus 6i squared all over 16 minus 2i squared. Difference of squares. On top, you've got 6i squared is negative 6. So I'll just go ahead and write it out so you don't get confused. You've got 8 plus 16i plus 6i squared. 6 times negative 1, so minus 6. And then on the bottom, you've got 16 minus 4i squared. So on the top, 8 minus 6 is 2, so you've got 2 plus 16i on the top. On the bottom, you've got 16 minus negative 4, because I squared is negative 1. So that's 4 times negative 1 on the bottom. So you've got 2. I always run out of room. 2 plus 16i on the top. And on the bottom, you've got 16 plus 4. So that's 2 plus 16i over 20. You can factor out a 2 on the top and the bottom. So on the top, you'd have 2 times 1 plus 8i. On the bottom, you have 2 times 10. So cancel the 2's because they're factors. This is multiplication. You have got to be careful about canceling things that are not factors. On the homework, I'm seeing people canceling, like in this problem, they might cancel the 2's. Okay, those 2's are not a factor of the numerator or the denominator. It has to be a factor of the whole numerator or the whole denominator before you can cancel it. All right, so this is almost the answer, but we have to write it real part first, imaginary part second. So 1/10 plus 8/10 I. That's going to be the final answer. Real part first, imaginary part second. All right, so writing complex numbers in standard form. I is equal to the square root of a negative 1. So every time you have a square root of a negative number, you have to write it in Euler's notation. You can't just leave it as square root of negative 5 and start multiplying things because it won't work. You have to change it to Euler's notation. So if you have the square root of negative 5, you write it as the square root of 5i. Then you can start doing multiplying, dividing, whatever. But don't start fooling around with these square roots of negative numbers. For example, here on part A, don't just start multiplying and say, oh, well, that's just equal to the square root of negative 3 times negative 12, which is positive 36, which is 6. No, that does not work. That is not what it is. Okay? You have to change it to Euler's notation, then you can do the math. So the first thing you do whenever you have a negative number under a square root sign is change it to Euler's notation. So the square root of negative 3 is the square root of 3i. The square root of negative 12 is the square root of 12i. Okay, now you can start doing some multiplication. You can rearrange it. Square root of 3 times square root of 12 times I squared, because I times I is I squared. Square root of 3 times the square root of 12 is the square root of 36. You're allowed to multiply two square roots, 3 times 12. If this was addition, you would not be able to do this. And I'm seeing people do that on their homework as well. You can't do this unless it is multiplication. The product of two square roots is equal to the square root of the products. This is not true for sums or differences. Be very careful what you're doing. All right, so that's the square root of 36i squared, which is going to be 6i squared, and I squared is -1, so the answer is -6. All right, you have to change it to Euler's notation. All right, in B, the square root of -48 is the square root of positive 48i, and then minus square root of 27i. All right, now you can't do anything with these because they're not like square roots. This is subtraction. All right, they have to be like terms. The square roots are not the same. Well, what do you need to do? You need to reduce the square roots. All right, you need to look for a perfect square in that square root. If you know that 16 is a factor of 48, you can write this as 16 times 3i, and then here the square root of 9 times 3i. All right, so this is the square root of 16 times the square root of 3 times I minus square root of 9 square root of 3i. All right, square root of 16 is 4 square root of 3i. Square root of 9 is 3 square root of 3i. Now you can subtract these. 4 square root of 3i minus 3 square root of 3i. You can factor out the square root of 3i. That's going to be 4 minus 3. So that's negative square root of 3i. Sorry, positive square root of 3i. 4 minus 3 is 1. So square root of 3i, you don't really have to factor out the square root of 3i, but I thought it might make it more clear to you. But 4 square root of 3i minus 3 square root of 3i is just 1 square root of 3i. Oops. All right. If you square a binomial, what do you have to do? Does this equal 1 plus -3? No, it does not. You can't do that. All right. This doesn't mean -1 squared plus square root of -3 squared. That's not what it means. It means -1 plus the square root of -3 times 1 plus, -1 plus the square root of -3. You have to multiply the binomial by itself. All right? Now, you can't do anything with this until you change it into Euler's notation. -1 plus the square root of 3i times -1 plus the square root of 3i. Now you can multiply it out. -1 times -1 is 1 minus square root of 3i minus square root of 3i plus square root of 3i squared. That's the last thing you multiply there. All right, so this is 1 minus 2 square root of 3i. You've got 2 of them. And then plus square root of 3i squared. That is plus 3i squared. Square root of 3 times square root of 3 is 3. All right, so 1 minus 2 square root of 3i. And then 3 times I squared is 3 times -1, which is -3. So 1 minus 3 is -2. Minus 2 square root of 3i. Real part, imaginary part. Real part here, imaginary part here. All right, so where do these numbers come up? They come up in all kinds of quadratics that don't turn out to have a positive number under the radical. So in this problem, we've got a quadratic equation. We've got everything on one side. We've got it set at equal to 0. We've got our a, we've got our b, we've got our c. So we can just start plugging it into the quadratic formula. So negative b, opposite of -2, is 2 plus or minus the square root of b squared, so that's 4, minus 4ac all over 2a. All right, so that's 2 plus or minus the square root of 4 minus 35. 4 minus 60. 4 times 3 is 12, times 5 is 60. And then on the bottom, you've got 6. All right, so 2 plus or minus the square root of -56 over 6. You have to change it to Euler's notation. 2 plus or minus the square root of 56i all over 6. And then you have to simplify the square root of 56. You have to think, what goes into 56? I know it is 8 times 7. 4, therefore, is a factor of 56. So 2 plus or minus the square root of 4 times 14i over 6. So you can take 2 plus or minus the square root of 2, square root of 14, I over 6. So I'm sorry, square root of 4. Just breaking up that square root into 2 square roots. So 2 plus or minus 2 square root of 14i all over 6. And now you can factor out a 2 on the top and the bottom. And again, I'm sorry, I'm going to have to take it way over here. I never leave enough room. So that would be 2 times 1 plus or minus the square root of 14i all over 2 times 3. So the 2's cancel, and I end up with 1/3 plus or minus the square root of 14i over 3. This would be your final answer. Those are the 2 solutions to that equation. And you've got your real part first, your imaginary part second. That's how you need to write it. Completely separate. Real part first, imaginary part second.